So a few months ago, I did a webinar talk for iTelescope, which they have a YouTube channel and a website and a whole bunch of other cool stuff that you should check out. I'll link them in the description box below. But anyway, I did a webinar talk for them about how studying Earth informs our search for life on other worlds, as well as just informs our understanding of other worlds, other planets, other moons, their geology, their potential for life, their chemistry, and all of that. And that webinar was posted on their YouTube channel, but I just feel like it didn't get, it's like an hour-long talk, so it didn't get as much traction as I would have hoped, and I think it's a really cool topic, and it's something I haven't specifically covered on this channel, so I want to today do like a 20-minute version of that talk. And after this, if you want to check out the hour-long live recorded version with question and answer session, you can check that out at their YouTube channel. I will link it in the description box below as well as my end screen. So anyway, with that said, let's get into the video. Earth and aliens. A lot of people think that our search for life on other worlds is independent from our study of Earth. But in fact, it entirely relies on our understanding of Earth, life on Earth, ancient life on Earth, and how conditions on Earth, especially conditions habitable for life, have formed and evolved through Earth's history and how life has evolved with it. So our understanding essentially of Earth's past and the evolution of Earth is what informs our search for life on other worlds. And that's what I'll be talking about and giving examples of in this video. And actually, I just want to preface this video with, I know a lot of you have expressed to me that you like the Earth-focused videos of mine more so than the astrobiology, life on other worlds type videos from me, but I just think this topic is so cool, and it's really hard to even separate, the study of Earth and other worlds because they're so reliant on each other, really. Actually, I will be talking about one particular example today of how not only is our study of Earth super important for studying other worlds, but also studying other worlds can help us study Earth. And I'll give an example of that later in this video that's super cool. So stick around even if you don't think this is your, vibe of a video. So first off, I just mentioned how studying Earth's past, in particular ancient life on Earth, is really important for studying life on other worlds. But how do we even start? How do we study ancient life on Earth? Well, we use the rock record. Before humans were around to study life on Earth, record information about the environment, rocks were around doing that for us. They were preserving signatures of life. They were preserving signatures of climate, environmental changes. All of these things are in the rock record. And what we use in the rock record are called proxies to do this. Proxies are just physical, chemical, and biological signatures in the rocks. For example, fossils would be a biological proxy, and so we'll go over a lot of these different proxies in today's video and talk about how they help us reconstruct ancient climates, ancient environments, and ancient ecosystems. So how I'm going to structure this video is talking about the three major types of proxies in the order physical, chemical, and then biological. And with each of these categories, I will go over both how we use them to study ancient Earth and examples of how we use them to study other worlds. Starting with physical proxies, these are things like sediment or rock texture, structure, composition. Well, composition can go into chemical as well, but sometimes can be physical if you're not looking deeply into the chemistry of the rock, but just looking surface level composition, like what's the color, the composition controls the color, all of that. So some of that can be physiochemical, I guess. There's crossover. But anyway, texture and structure are also really important, and these types of physical features preserved in rocks are dependent on climate and environmental conditions. And when climate and environmental conditions change in a particular region, this physically alters rocks and sediment in a predictable way, and thus we can use these proxies to study ancient climatic and environmental conditions. For example, structures in sedimentary rocks, which are called sedimentary structures, I know, super original, are really helpful for reconstructing past environments, so the local environment in which those rocks formed. We can see this, for example, in this sandstone picture to the right. This is a huge sandstone outcrop with these diagonal kind of curvy lines preserved in it. These diagonal curvy lines are what we call cross-bedding. And cross-bedding structures indicate to us, well, if they're preserved in sandstone, that is purely sand, this is where composition comes into play. If cross-bedding is preserved in pure sandstone, it indicates to us, most likely, sand dune formation. And sand dunes, where do sand dunes form? Well, they form in desert, or what we call aeolian environments. In the direction of the cross-bedding, in this case it's diagonal downward to the right of the screen, that indicates to us that the wind was traveling that way, because we know how dunes form today and how the particles move in a way that creates the cross-bedding slanted down in the direction of the wind. Similar cross-bedding structures can be formed in other compositions of rocks, like more interbedded mud and sandstone rather than just pure sandstone. And when we have different compositions with cross-bedding, that indicates potentially a different environment. For example, instead of wind transport, it might be water transport. But anyway, the point is, structures like these can be really helpful for studying past what we call depositional environments, the environment in which the sediment was deposited. And I have a whole playlist that focuses on depositional environments, and I actually have a whole video talking about sedimentary structures and their corresponding depositional environments, or likely depositional environments, which I will link to the top right if you are interested. So what about structures and other physical proxies on other worlds? Well, we actually see a lot of water indicating structures on Mars, like ancient channels and ripple marks and cross-bedding in sediment on Mars, which likely indicates the past flowing of water on Mars's surface. Note here, water, as we'll talk about later throughout the video as well, is very important for our search for life on other worlds, because at least life as we know it, life on Earth, requires water. A lot of people and a lot of poppy titled articles always say, oh my gosh, this exoplanet or this whatever has been found to have oxygen on it, so maybe there's life there. Well, oxygen is not nearly the most important thing for life. Oxygen as an element is important for life, as is carbon, hydrogen, phosphorus, and sulfur, at least life as we know it. But oxygen as a molecule, O2, the thing that we breathe that's in our atmosphere, that is not required for all life on Earth, nor was it required for the first billion plus years of life on Earth. It wasn't until 2.4-ish billion years that oxygen even started being produced by photosynthesizers to an extent that it could then be used by life, eventually once life evolved the ability to use it in metabolism, which eventually led to us animals to be able to metabolize or use oxygen to gain energy. That is actually something that came along later. All life before that didn't use oxygen. In fact, there's a lot of bacteria, microbes that were and still are intolerant to oxygen. They hate it. They don't like it. These microbes live in a lot of deep, dark corners of sediment in the ocean, in soils, even in our own guts. So life on other worlds doesn't require oxygen. The point is, water, on the other hand, is very important. And speaking of water, if you've been following my channel for a while, you probably know that there are many moons of Jupiter and Saturn that have a lot of water. They are ice-covered moons that below a surface crust of ice have liquid water oceans. An example of this is Europa, and Europa actually also has physical structures at its surface that we can use to understand its large-scale geology and whether potentially any liquid water ever makes its way to the surface. And that, as I'll talk about later, is very important for this moon's habitability. So before I jump right into Europa, if you don't know, Europa is a moon of Jupiter that again has an ice-covered liquid water ocean and physical surface features that we can see here on the right, which make it look kind of cantaloupe-ish, that hint at what is below. One example of a really exciting feature on Europa are its dilation bands. These bands might be analogous to moors or mid-ocean ridges on Earth. Mid-ocean ridges on Earth are where plates, tectonic plates, are pulling apart. They're undergoing extensional stress because of the mantle upwelling beneath them, and the mantle material, eventually forming a melt and magma, comes up to the surface and comes out as new crust on Earth. So is Earth expanding? No. There are subduction zones where tectonic plates go under continental crust and get destroyed and recycled back into the mantle. And these two processes keep Earth's tectonic plates, moving. Like mid-ocean ridges on Earth, these dilation bands on Europa are raised relative to their surrounding plains, and they have consistently spaced lineaments, so liney features, that suggest dilation episodes, just like on Earth. So essentially, mid-ocean ridges represent episodes of new crustal production during episodes of mantle upwelling and magmatism at those ridges. And those are kind of protracted episodes that create these linear features, these lineaments along mid-ocean ridges that are dated younger and younger and younger as you go toward the center of the ridge. And dilation bands on Europa seem to be similar. But what exactly would be the mantle for Europa? It's not magma, it's not rock, it's an ice crust. So is the magma water? Well, not necessarily. The ice crust of Europa is so thick, it actually is thought that deeper and deeper you go, it gets kind of like our own rock mantle, which isn't liquid, but it does convect, and it does eventually upwell and lead to melting and magma that forms and rises and causes volcanism and magmatism at Earth's surface. Well, similar to that, this icy crust on Europa, which also, like our own mantle, is rock, just instead of silicate, it's H2O. And so this icy mantle of Europa might convect in some places, even though it's solid, and lead to similar magmatism on Europa that is driven by ice and water instead of silicate rock and melted silicate rock. So if there's dilation bands on Europa, are there features analogous to subduction zones on Earth? We think maybe, yeah. These are called subsumption bands. And this is where, just like on Earth, where denser plates subduct under less dense plates, we think that maybe icy plates that are denser than other icy plates subduct under those less dense plates. We think this could be possible because there could be density differences in the icy crust, throughout the icy crust, driven by differences in salt content. And this could be super critical for life on Europa because subducting ice plates could deliver surface material to the ocean. Just like plates get subducted back into the mantle on Earth, these ice plates, if they get deep enough to get all the way to the liquid water ocean, could recycle material that has food for life back into the ocean. I talk about this concept of having a relatively open rather than closed system in the liquid water ocean of Europa and other ice-covered ocean moons in my Europa geology video, which I'll link to the top right. It's super important because if there's no recycling of surface material back into the ocean, then Europa's ocean might represent a relatively closed system in which chemicals that are food for life can be converted one way, but not the other way. Like, imagine that if our atmosphere was a closed system and oxygen that we need to breathe was not reproduced, recycled in any way, we would just breathe it all up and then die. Like, we would just use it all up, convert it to CO2, and then die. If there's nothing to reconvert that molecule to what we need to breathe, then we'll just use it all up. Same thing with like a closed system, scenario on Europa. Yes, it's possible that there's life that could do the opposite reaction. So for example, for us, that's plants. They convert the CO2 back to oxygen. And so we have this cycle between photosynthesizing organisms and respiring organisms like ourselves. And so that's possible in Europa's ocean, but for life to get started, the open system, geologically active type of scenario makes it way more likely that life would have gotten started to form ecosystems where they are more self-sustaining like we have on Earth today. So that's it for physical proxies. Now moving to chemical proxies. Wow, this is going to be a longer video than I thought. Rocks preserve chemical signatures, so signatures within their composition that we can look at, which I'll explain in a second, that result from very specific temperature, pressure, and pH conditions and other chemical conditions in which they form. Ocean chemistry, like temperature, pressure, pH, salinity, what types of ions, salts are around, calcium, sodium, potassium, all of these things. This chemistry and changes in ocean chemistry locally and regionally control marine rock and shell composition. One example of a type of chemical proxy that is super useful when it comes to reconstructing past conditions in chemistry and whatnot are stable isotopes. Stable isotopes, unlike what you've probably heard of, which are radioactive isotopes or radioisotopes, do not decay like their radioactive cousins, which is why we call them stable. I have a video talking about the differences and the different uses of stable versus radioactive isotopes, which I'll link to the top right if you're interested in going deeper, because I'm not going to go very deep into it and how it all works in this video. Just some brief information about isotopes is that they are atoms of the same element that have different number of neutrons, and thus different mass. Neutrons add mass to the atom. And so stable isotope ratios in rocks represent paleoclimate or ancient climate because climate change alters the distribution of these isotopes because they fractionate or distribute themselves differently in different environmental systems depending on their mass. For example, when climate is overall warmer, more water evaporates from the ocean and goes into the atmosphere as water vapor, and this water vapor contains more of the heavier oxygen isotope compared to cooler periods in Earth's history when the ocean is much less evaporative and therefore pretty much only the lighter isotope of oxygen, or the water containing the lighter isotope, evaporates and forms the water vapor in the atmosphere as opposed to the heavier signature we see during periods of warming. In any case, this is just one example. Another example, though, especially more applicable example to today's video and the topic of life, is the use of carbon isotope signatures in the rock record to indicate ancient or even extant life. The reason carbon isotopes are super useful for studying ancient life on Earth is because plants and other photosynthesizing organisms preferentially take up light carbon, so carbon-12 stable isotopes, rather than carbon-13 in terms of the carbon dioxide they take up. Therefore, organic carbon deposits produced by such photosynthesizers preserve lower carbon-13 to carbon-12 isotope ratios than inorganic carbon-containing rocks. We can actually use this preferential uptake of carbon-12 light carbon isotopes by life to determine what the first life on Earth was. There is an Archean-aged graphite formation in Greenland, the Ishua Formation, that is about 3.9 billion years old that has a very low ratio of carbon-13 to 12 isotopes in it. And this may represent the oldest signature of life on Earth. But it needs a little bit more corroborating before we can absolutely say, yes, there was carbon uptaking life 3.9 billion years ago. We do think that life probably evolved before 3.5 billion years ago, but 3.5 billion years ago is just about the most robust fossil evidence that we have for ancient life, and thus we kind of can't go back further than that without using a bit of speculation. That said, the carbon isotopes is kind of the first step in warranting further exploration of more ancient rocks. But anyway, on to now our example of applying isotopes and other chemical proxies to searching for life on other worlds. Can these isotope signatures be used to look for life on other worlds? Well, absolutely. A couple examples of, again, moons of Saturn this time instead of Jupiter like Europa. We have Enceladus and Titan, which also contain ice-covered liquid water oceans. Titan also has huge lakes or kind of oceans of methane at its surface, but this liquid methane is not water, and when we look again for life as we know it, we tend to try and look for water, and so we focus a little bit more on its subsurface ocean. But Enceladus actually has liquid water plumes at its south pole, so plumes of water that shoot out from its south pole in addition to its liquid water ocean underneath. And this surface breaching of the liquid water at its south pole is really important for the cycling, potential geologic cycling we were talking about for Europa earlier, which helps sustain life. The reason these plumes are super important is because they indicate hydrothermal activity in the ocean beneath them. This is important for two reasons. Hydrothermal water-rock interactions, so really hot water-rock interactions deep in Enceladus's liquid water ocean, might create enough chemicals and a variety of enough chemicals in enough forms to support life. And two, we can sample it. Because this drives plumes of water coming out the surface of Enceladus, we can actually sample that plume material to get a sense of what chemicals are in there and whether any of these chemicals represent a metabolic pair, in other words, a pair of chemicals or molecules that can be used for life to metabolize or create energy and maintain themselves. So what might we find when we look in these plumes? Well, actually, Cassini has already sampled them and found that they contain molecular hydrogen, carbon dioxide, methane, and other organic molecules. Organic molecules often get, the eye-opening reaction of, oh, that means life, but it doesn't necessarily. Organic molecules can form abiotically, so we can't just use that to say, yes, there is life. However, this mixture of chemicals is actually really interesting as it does represent a metabolic pair and product pair. In other words, carbon dioxide and molecular hydrogen are often used on Earth by methanogens, microbes that produce methane, using these molecules. And this reaction produces energy for these methanogens. But how exactly can we tell if the methane produced on Enceladus is biotic or abiotic? Is it produced by life or is it produced abiotically? It can form either way. Well, a 2021 paper came out with a model that suggests the biotic methane scenario, in which it's biologically produced by life in Enceladus's ocean, is most likely assuming the probability for an origin of life event is over 35%. In other words, if an origin of life event is somewhat likely to happen in a habitable environment, yeah, the methane's probably produced by life, but how the heck do we know the likelihood of an origin of life event in a habitable environment? Again, it all comes back to Earth and studying Earth. We don't know yet where, how, or how long exactly Earth's origin of life took. So therefore, it's pretty easy for us to judge if an environment on another world is habitable, in other words, supports life as we know it, because we know what life as we know it needs to live, but we can't yet judge very well whether an environment can support an origin of life event. Earth's origin of life may have occurred at a hydrothermal vent deep in the ocean, or it might have occurred at the surface. We don't really know exactly where Earth's origin of life event occurred. What we do know is that a surface origin of life on Enceladus is not possible, at least in Enceladus's current state. And so if we could figure out where Earth's origin of life event occurred, if it was deep in the ocean or if it was on the surface, this would help us say whether or not an origin of life event on Enceladus is more likely or less likely. But not only is studying Earth's past and origin of life helpful for predicting life on other worlds like Enceladus, looking for life on other worlds and confirming separate origin of life events is super helpful for understanding Earth and its origin of life. Because just one more origin of life data point would give us a whole bunch more information about our own. But now moving on to biological proxies, which will cover another method that we can use to confirm whether the methane on Enceladus is biological or not, a method other than just modeling. Fossils are the first thing we think about when it comes to biological proxies in Earth's rock record, but these aren't yet applicable to astrobiology or life on other worlds, at least not yet. Why? Well, because we just haven't found any. But there are potential biomarkers and biosignatures that might be useful in searching for extraterrestrial life. The light carbon-12 rich isotope signature that we talked about earlier, which indicates the presence of photosynthetic life, is an example of a biosignature. Biomarkers, though, are a little bit more direct indicators of life, but are often a bit less robust and harder to get preserved. They're relatively resistant organic molecules unique to a specific organism or group of organisms, and their abundance can be used as a proxy for past distribution and abundance of their source organisms. For example, hapenoids are a type of biomarker organic molecule that form in certain bacteria, lichens, ferns, trees, and fungi, whereas steroids are biomarkers typical of animals. So because different taxa, different groups, contain different structures, different biomarkers, we can identify the presence of specific organisms or their groups in Earth's past using biomarkers. And the use and study of biosignatures and biomarkers on Earth, how they form, what they are, what gets preserved, why, provides us a basis for searching for life on other worlds. For example, again with the biosignatures, if we found that the plumes of Enceladus contain very light carbon isotope ratios, it could indicate to us the presence of life, because even methanogens, which take carbon dioxide to produce methane, do preferentially take up light carbon isotopes, therefore would produce relatively isotopically light methane. So that could be a signature that could indicate to us that it's biological rather than abiotic. Likewise, if we found hapenoids or some other biomarker on Enceladus or in its plumes within the organic matter that we find in the plumes, this could be even more robust evidence for life on that moon. So in other words, and in summary, Earth is our laboratory on which we can study how to explore the universe. So I hope you guys enjoyed this video, and if you want to check out the long recorded live version with question and answer session at the end, you can check that out. I will put it up here on the screen somewhere. And also check out iTelescope. They'll be linked in my description box below, and you can also check out their YouTube channel once you click on the video that is on their YouTube channel. But anyway, I hope you guys enjoyed. References will be linked down below as always, and I will see you guys in my next one. Bye!